Okay, there we go. Okay, so I've got some line integral problems. I actually lied. I don't have any work problems for today. I got too caught up in the line integral problems, so no work problems. But we got computing. Oh, hey, Catherine. So we've got computing some potential functions for some curve, basically like how you can find them. There's a few different ways, and we'll set up and compute a lot of different line integrals. And we'll see how much material we've got to get through today. It probably won't be full 50 minutes. We'll see. See how much time we need to
Before we go
solve some of
much
these
further, I
problems.
have a question.
Yeah,
So what was the difference between the line integrals we did today and the line integrals we did on Monday?
that's a great question. And actually, we'll get to that as we go through this. I promise. I'll answer your question. Let's talk about that. So by the end of the session, I figured I'd show this. We hope to solve this guy. This is from like an exam review question. Um, kind of just so you can see what's coming. You guys will hopefully be able to do this one on your own by the end of the session. So what we've learned so far. So that's a great question. So we've learned three flavors of line integrals, right? It's kind of like I knew you were going to ask that question. The first one was where we had like a function of f and y, x and y, and it had like a ds, right, and a c. And we used the whole ds is equal to the square root x prime squared plus y prime squared plus z prime squared dt, right? That was the first one we solved. And that's when we just basically had a function in terms of x and y in here with a ds on the end of it. That's when we would use this ds equation. When you see the ds, that's your cue to kick it into the Pythagorean's theorem kind of deal there. The next one we learned, it was basically like the m dx plus the n dy, and these were kind of like our work problems, if you remember those. And there's two types of these problems, so that's why I said there's three. There's this guy, which is one, and then there's two other types that are kind of under the same umbrella. There's one where it's conservative, right? Um, that's when your m of y is equal to your m n of x, and that's what we talked about if you watched Butler's lecture that was on finding the potential functions. That's what the conservative did. And if you have a conservative function, you just take your starting point, like x2, x1, and you subtract it from, oh, sorry, that should be y over here. You subtract it from your starting point, kind of just like a regular integral. So that's if its function is conservative, that's what we care about. Because remember, we have like line integrals, and you have your line integral moving all over sorts of space. Um, But if your function is conservative, this line that goes all the way out into space is equal to the same line that connects them by the shortest path. So that's why we can use this equation if it's a conservative, and that's why we talk about vector fields, and that's kind of something that's big in fluid flow is conservative vector fields are cool because as long as you find the potential between those points, it doesn't matter what path you follow to find that potential, it's always going to be the same. And that's why we can use this really simple, just plug the point into the potential function at the start and ending points, and that's how you get it. If it's not conservative, that's where it gets a little trickier. Maybe it's not trickier, depending on the problem. But that's when we have to basically like pull from our problem, right, our x, and we turn it into the x sub t, and then we have our y, which is like our y sub t, and then we find like x prime and y prime, and that's when we plug all of that into the equation. So we have m dx plus n dy, and then we have to plug in basically everything into our function, right? And we'll talk about all these different types of problems. I don't think we'll do any of these. We've done a lot of those, but we'll do a lot of these two types of problems and distinguish between them for today. So
When did he talk about the not conservative ones? 'Cause I know that on the last page of his notes, like the last what 10 or so minutes, he was just talking. He's like, you don't know, you don't have to know this, but this is something. But I don't know if we did any examples with non-conservative ones. I'm
yes,
not.
um, yes, we did some of them in our session on Monday, and I'll post that to the YouTube page. I still have that one on my computer. I'll be posting that one in this one tonight. But we'll do a problem where you solve this kind of problem as well. Um, we'll solve a problem in this form today. So we'll talk about how to actually do the math. Because I remember he didn't talk about how to do the math, which was kind of weird. But he does, when you go in and watch his exam review stuff, he definitely solves some problems for you. So if you want to see Butler solve some problems, you can watch his exam reviews. Oh, Caleb, I'll link it at the end of the session for you. Caleb is asking what's the YouTube page is called. So I'll put a link in the end, and I also put it on the. I don't think the link is on the website now. I'll put the link on the website too. But yeah, all right, cool. So I'm recording this one as well. So yeah, it can't see the chat or anything. It can only see the screen about what I'm doing. So all right, so let's look at this. So we have this curve here, t squared. 0 is less than or equal to t, which is less than or equal to 1. Find the line integral of y plus x squared dx plus ex to the second dy. Okay, so let's think about this. Let's talk about this. Is this conservative? Question mark. So to find conservative, right, it's m of y is equal to n of x. So we can use, basically our m of y is going to be 1. And our n of x is, let's see, we can't find, I don't really want to solve that, but it's not equal to 1, right? We know that for sure. So this is not a conservative function. So what we have to do is substitute in the parameterizations and solve it that way, kind of like we talked about above, where we basically have to plug in everything. It's this form. So we did a lot of these on, I guess today's Wednesday, so we did them on Monday. Let's do one now, and I'll do it in front of you guys so you can kind of get a feel for what's going on. So we have to substitute in the parameterizations. So what we have, the information we're given up here is x is equal to t, y is equal to t squared. And from that we can find x prime is equal to 1, take the derivative with respect to t, and y prime is equal to 2t. So now we take all of this information and we plug it into our original equation. So we take all of it, I'll do it in another color. So I guess we solve them. I've got a section down here just for us. So let's plug it all in. We've got y plus x squared. So if we plug in what we know about y and x, it'll become t squared, which is y, plus our x is a t, and we square that again, squared. Dx is just x prime, which is just 1. And then we've got plus, okay, e to the x squared. So x is t, so it'll be e to the t squared. And then at the end of this, we just slap on a dt. I'm not kidding, that's how Butler talks about it. We just slap it on a dt at the end of it there. So now we just solve that integral. Of course, we're going from t is equal to 0 to t is equal to 1. I forgot to put that down.
Don't forget dy.
dy. Oh, dy. Yeah. Thank you. Woo. So times 2t. Yeah, the u substitution would have worked. Awesome. And then we got the dt. Good catch, Nathan. Cool. And now we just solve that. I mean, I can solve it out for you guys if you want. It'll go 0 to 1. It'll be a 2t squared plus 2t e to the t squared dt. And then after we take that, we can see some u substitution in there. So we'll have, take the integral of all of it. It'll be a 2/3 t cubed plus, we'll say u is equal to t squared, du is equal to 2t. Okay, that's pretty easy. So then we'll get, I guess it would just be e to the t squared, wouldn't it? Evaluate all that from 0 to 1. When we evaluate from 0 to 1, we'll get 2/3 plus e minus 1, which is, I think it's e minus 1/3. So yeah. Big important stuff here though, not necessarily in the algebra. Are there any questions about that? Awesome. All right, cool. So that's how we would solve non-conservative functions. Basically, just take what you know, solve for your dx and your dy, plug everything in, slap a dt on it, and solve the integral. So now let's compare this to something maybe conservative. The curve is starting at 0, 0 and going to 1, 1. So is this conservative? We can say conservative means that my is equal to nx. So my will be 1, perfect, which is equal to nx, which is 1. So yes, it is conservative. Okay, so when it's conservative, what we want to do, remember, because if it's conservative, that's important because now we can just take the potential function at 1, 1 minus the potential function at 0, 0, and that is how we find our integral. So it's a lot easier way than solving out the whole integral. We can just basically find what our potential function is, and then find the difference between the potential function at 1, 1 and 0, 0. And that's why we care that it's conservative. It's a conservative vector field. So let's find the potential function. We talked about how to do this today, and we'll do a lot of this as well. So to find the potential function, there's a couple ways you could do it. You could either do it by cascading integrals, or you could do it by kind of like the guess and check method, which was a pretty interesting one. And honestly, I wish they didn't teach this when I took the class, to be honest. But basically what they say is find your m, and what you do is just take the integral of it with respect to x. So we take the integral of our m with respect to x, what we'll get is xy. And now take your n and take the integral of it with respect to y. So if we do that, we'll get xy. Cool. And now what we do is we basically combine everything for a potential function. So it's got xy and xy. They're the same thing, right? If they're the same thing, we can combine it. So our potential function is just xy. And don't worry, we'll do a lot of these today. So do not worry one bit about it. So we found our potential function, which is xy. And after we found our potential function, now we just solve, right? Now we just say that our line integral, c of y dx plus x dy, right? We solve all of that is just equal to f of 1, 1 minus f of 0, 0, which is just equal to 1. Sweet. Are there any questions about that? Sweet. Awesome. So let's do your turn. You don't have to we're not going to find an integral this time, but try to find the potential function, kind of like I did last time. Take your first function and integrate it with respect to x. Take your second function, your m, integrate it with respect to y. Combine your terms and see what potential function you get. I'll give you guys 3 minutes. I'll start a timer for 3 minutes, and then I'll come back to you and see how you do. Good luck. All right, cool. So I'm getting answers from Caleb and Nathan. They got the same thing. Yeah, sweet. Let's do it, and we'll see if we all got the same thing. So we'll take the integral with respect to x. So we've got x cubed y squared plus e to the x. They made that easy. And then our second one is we'll take the integral with respect to y. So we'll get x cubed y squared, perfect, plus negative cosine of y. And if we combine those together, we get x cubed y squared plus e to the x minus cosine of y. Nice job, guys. Awesome. Cool. Oh, you should have a minus cosine. Or am I wrong with my minus for the integral? Let's see. We've got, so if you have sine, so the derivative of sine is cosine, so that means the derivative of cosine is sine, so we're going in that direction. Negative sine. Yeah, it's got to be a negative cosine, doesn't it? So it should be a negative cosine.
Yeah.
Awesome. Cool. Awesome. All right. Oh, so let's have you guys try this one now. We'll have you guys try another one. This one's from the quiz, actually. So they want you to find the potential function. It's a little trickier. You have to be a little more cautious when you combine all of your like terms. But yeah, remember this will just be dx. This will be with respect to y. And this will be with respect to z. It's kind of like partial derivatives, but backwards and informal. All right, cool. I'll set a timer for 3 more minutes. We'll see how you guys do. Good luck. All right, sweet. So we're getting some good answers in the chat. So let's do this all really quickly, and then we'll move on because obviously we've got this down pretty good. So we've got from our x term, we've got, if you take the integral of it with respect to x, we will get x squared yz plus x to the cubed z plus e to the x. If we do that with our y term, our y term is a little smaller than that. will get x squared yz, perfect, plus 1/2 y squared. Okay, awesome. And if we do our z, we will get, with respect to z, we get x squared yz. I've seen that term before. Then we get plus x cubed z, perfect, plus arctan z. Awesome. Now, all we have to do is combine the terms that make sense, and our final answer will be, I'll do it in a nice new color, x squared yz plus x cubed z plus e to the x plus 1/2 y squared plus arctan of z. Awesome. Nice job, guys. That looks good. All right, so we're pretty good at finding potential functions. So that'll be useful when we have conservative integrals and we want to basically solve those conservative integrals. So let's move down to maybe a problem where we can try that. So say we have this function right here, and for 0 is less than or equal to t is less than or equal to 1/2 pi, we're given our curve, c. You can see we're just dealing with x and y in this problem and no z. Is this function conservative? And if it is, find the potential function. And remember, once we have the potential function, we'll take f, like of x and y, minus f of x naught, y naught. So we'll need an x and y point, and because we only have the bounds for t, we have to plug those t into our original equation, find that x point and y point, and then solve that. So let's do this together. Is this conservative? M of y is equal to n of x. So we'll get, let's see, we get y, we'll get e to the x is equal to, because I just did that, there's no y term in there, so that goes away. There's no x term in there, so that goes away. Take the derivative, so we'll get e to the x. Yes, it is conservative. Awesome. All right, so let's have you guys solve for the potential function. So you're looking for that little f. After you solve for the potential function, see if you can find that starting and ending point. You just plug your t into here, find your x and your y. And then after you do that, just solve for your final value. We'll see what you guys get. I'll let you guys loose for another, let's say 4 or 5 minutes on this one. And yeah, if you guys get a potential function and it's not too crazy, go ahead and throw it in the chat. I'm looking for what my solution would be right now, but yeah, if it's not too crazy to type out, go ahead and try throwing it in the chat. Otherwise, just keep working through it. I'll start a timer for 4 minutes, and good luck. All right, let's see how you guys are doing. Nathan has got negative natural log of 2 minus 5. So I have the same exact thing, but I have opposite signs. So let's run the problem down, and we'll see how well we do together. I don't even think we need to solve for the potential function. You guys nailed the potential function right on the head. We got y(e) to the x minus x squared plus the natural log of 1 plus y squared. That was awesome to see that. So now we need to see if we can find the starting and the ending points. So let's do that. So we have basically plugging in 0. Let's start with 0. T is equal to, my computer doesn't want to work today. T is equal to 0. So we'll get 2 times the cosine of 0 plus 1 over 10, the sine of 20 times 0, comma, the sine of 0, plus 1 over 10 sine of 20 times 0. Okay, so let's see that. So we'll get, I guess we could, this will be cosine of 0 is 1. So we'll get 2 plus, okay, sine of 0 is 0. Perfect. So we'll get 2, comma. The sine of 0 is 0. And then we'll get plus 1/10 times the sine of 0, which is 0. So we'll get 2, 0 for t is equal to 0. Okay, now let's try t is equal to, what's our other t? 1/2 pi. So if we plug that in, we'll get 2 times the cosine of pi over 2 plus 1 over 10, the sine of 20 times 1 over 2 pi. Okay, that'll be interesting. Comma, the sine of 0. Oh, sorry, not the sine of 0. We'll get the sine of pi over 2 plus 1 over 10 sine of 20 times pi over 2. And we'll close that parentheses. Okay, so we've got the cosine of pi over 2. Cosine of pi over 2 is just 0. Plus, okay, 1/10 sine of 20 pi over 2. So the sine of 10 pi. So it'll be 1/10 sine of 10 pi. If I've got that correctly. Sine of 20. Yep, that looks good. So the sine of 10 pi, anybody in the chat, we have what sine of 10 pi is equal to? 0. Nathan says 0. Any other answers? 1 from Caleb. Anybody else? Okay, yeah. Well, I'm going to take a guess and say it's between 0 and 1. Okay, so we've got, remember, we'll go from, we'll just basically 10 pi. So 2 pi is 360 degrees. So if we divide it by 2 pi, then we'll get 5. That doesn't really make sense. So let's look at it more so in a circular term. So we start at 0. So we'll go 2 pi, which is 360. Then we'll go another 2 pi. Then we'll go another 2 pi. So now we're at a total of, so we did 2 pi, 2 pi, 2 pi. So we're at 6 pi. Do another, that's 8 pi, 10 pi. So we're at basically right here. The y-coordinate of the sine of that is 0, so that'll be 0. Okay, so now we've got 0. So I'll just write 0, comma, and then we've got the sine of pi over 2. Sine of pi over 2 is 1. Oh, we got a different number now. And then we know that the sine of 10 pi is 0. So now we get a total of 0, comma 1. Sweet. Okay, now that we've got our points, now we just have to solve the line integral by plugging those points into our original equation. So we'll do, now that we're solving f of our first point, so we're going from 0. 0 we go is 2, 0, minus our second point, which is 0, 1. So now that is equal to, so our potential function will be, we just have to keep all of our x's and y's straight here. So we'll have a 0 because that's a y, minus x squared, so it'll be 4, plus the natural log of 1 plus y squared, so the natural log of 1 is 0, so we'll put 0, minus our next one, so we'll get minus, okay, so we've got our potential function, which is y e to the x. So we'll plug in y of 1 and x of 0. So we'll get 1, and then we'll get, let's see, a lot of things to keep straight. X squared, so we'll plug in 0, we get a 0 minus, and then we'll get a natural log plus natural log of y squared, so it'd be 5. Sweet. So we'll get negative 4 minus 1 minus the natural log of 5. So you're right, Nathan. My signs were incorrect. So we'll get negative 5 minus the natural log of 5. Awesome. Are there any questions about that one? Sweet. All right. Nice job, Nathan. So let's press on. This was an interesting problem I ran across. Always remember what conservative means, because when we solve for something and prove it's conservative, that is significant. So is our function, so we're trying to solve, we've got a really nasty curve here. It'd be fun to plot that curve if we wanted to in like MATLAB or Wolfram Alpha or something. T is less than or greater than 0 and less than 1. And we've got this nasty function here. So let's first prove if it's conservative. We got my is equal to nx. So that says that our my will be 2x. And then our nx will be 2x. So yes, conservative. Okay, so we proved that it's conservative. What does that mean graphically? And I kind of showed you guys before. This just has an x and a y and no z in it. So maybe I'll do this in black. So if we have a function, it's starting at some point, and I'll save you guys the pain. It starts at 0, 0, and then it goes to, I think, 1, 0. If we plugged in our t into both, yeah. So if we plugged in our t, it would start at 0, 0 and go to 1, 0. But the curve just, is crazy. It's the e to the t squared minus t minus cosine of 2 pi t, and if you graph that whole thing, it'd be kind of weird. But because it's conservative, we know that this whole root is the same exact thing as this right here. So we might have seen in Butler's lectures, you can basically rewrite the curve if you want to make your life easier. So we could rewrite the curve. Let's rewrite the curve. So see, our x never changes if we go up the y-axis. So if our x never changes, it's never going to change with time. In our y, it changes linearly with time, right? It goes from 0 to 1. So at t is equal to 1, it'll be 1. At t is equal to 0, it will be 0. So we can just write t for our c. So instead of using this nasty curve, what we can do is just say that c is 0, t. Because it's conservative and we can rewrite the curve. It doesn't matter how we get to 1, 0. As long as we get there on a line in this conservative vector field, it'll be the same answer when we solve this line integral. So now that we have our c there, what I would suggest doing is treat it like an unconservative problem when we solved it in our problem style. So find your x. Well, I guess I'll do it in another color. Find your x, find your y. Our x is equal to, right, 0. Our y is equal to t. So our x prime is equal to 0. Our y prime is equal to 1. And now take your, basically your guy right here, 2xy plus e to the negative x squared dx plus x squared plus y cosine pi over 2 y squared dy. And now solve this like we would that original function, because solving it like it's not a conservative function is always going to work. Solving it where you always plug in the dx's and the dy's, as long as you can do that, it will work. So because I didn't let you guys do one of these, I'm going to let you do this one. Plug in your x prime, plug in your x's, plug in your y's, and see what you get. Our bounds are from 0 to 1. And I'll set a timer for another 4 minutes, and we'll see how well you guys do. Good luck.
Brian, I was gonna say, I think you were actually right on that problem the first time.
Oh, up above?
Yeah.
Oh, shoot. All right, let's go after it after this problem. We'll go look at it. All right, cool. So let's see how you guys did on this one. Nathan says he got 0. I did not get 0 the first time I did it, so, but I'm always usually wrong anyway, so let's try to prove that. Let's look at it. Actually, just kidding. Let's go back and look at that old one. You were right, Nathan. I did get it right. Because this is t is equal to 0. Oh, I want red. This is t is equal to 0, and this is t is equal to 1/2 pi. We need to flip-flop these, so it should be f of 0, 1 minus f of 2, 0, which is equal to 5 plus the natural log of 5. That is the correct one. This is incorrect. Awesome. Good catch. Okay. So let's look at this now. So we plug in basically everything that we want. So it'll be 0 to 1. We'll get 2 times 0. Okay, that's pretty easy. Y is t, but we don't need to do it. Plus e to the negative 0 times dx, which is 0. So this whole thing goes away anyways. Plus, okay, so we've got x squared, which is 0. Plus y is t times cosine of, we'll get pi over 2 times t squared. Okay. And then we'll get dy. dy is 1 dt. So this integral will turn into 0 to 1 of t cosine of pi halves t squared dt. Okay. And now to solve this, we'll probably need a little bit of u substitution. That might help us out the most. So a little bit of u substitution, u is equal to pi over 2 t squared. Du will equal pi t dt. And then, so it'll be du over pi is equal to t dt, and that'll be right here. And now we solve this guy with, we'll have to do the u substitution, so it'll go 0 to pi over 2. And then we've got cosine of u du over pi. So it'll be 1 over pi times the integral of cosine, which is negative sine. Is that correct? Oh, just kidding. It'll be positive sine, won't it? So sine of u evaluated from 0 to pi over 2, which will just be pi, 1 over pi. Sweet. Are there any questions about that one? Awesome. All right, cool. Well, we didn't get to do this, and I even had a great meme for it, but that's okay. It's 5:58, and I know there's a physics exam tonight, so we'll let you be going. You can actually find this on practice exam problems. It's the worksheet B, if you want to find it. I'm sure we'll find it as we move into exam season. But yeah, that is all I have for today.